After graduating, he then spent 3 years working in education as a learning skills advisor and a secondary instructor for the Academic Excellence ACE program at USC.
There's seats over here. The seats.
Providing extra support for typically underrepresented students in calculus and introductory physics courses. Donez is currently a PhD candidate in physics at UC Berkeley, studying low temperature properties of amorphous metal-oxide films with Professor Francis Howman. He's also an active member of the Access Network and also Compass, which is a group of students, faculty, professionals from universities across the country dedicated to fostering a more diverse, equitable, inclusive, and accessible, that's too many words, that community. In his free time, Donnie enjoys playing music, and he serves as the principal bassoonist, of the UC Berkeley Symphony Orchestra. Thank you.
All right. So thank you for the nice introduction. I'm excited to be here. I wanted to take a couple of minutes before I actually start the talk to just kind of acknowledge the Compass Project and the Compass Lectures. So the Compass Project has been around for almost 2 decades at this point, and one of the early initiatives that they had was making research done at UC Berkeley accessible to undergrads. And so they started, the early founders of the Compass Project started this Compass Lecture Series as a way to explain this to you guys, to show you what work is being done in the labs on campus that you're not going to actually see in your classrooms. And so after several years, the lecture series went into a hiatus. There were lots of changes in the administration and bureaucracy and lots of other issues. And so when I came here for graduate school and I joined the Compass Project, I knew that this was something that was very interesting to me. As Moore said, I worked in education before coming to graduate school. So undergrad education and kind of getting undergrads involved in research is something that's really important to me. And so back in 2018, I wanted to restart this lecture series because I thought it was something that would be really beneficial to the physical sciences here at Cal. And so I'm really happy to see that at the beginning, when I first restarted this lecture series, it was just me by myself, kind of coordinating everything. It was very bare bones. There wasn't a lot of snacks and a lot of like fancy Zoom links and everything like that. But over time, we've gotten more people involved, and we have lots of people who have been keeping this lecture series going. And I've been slowly, as I'm getting close to graduation, I've been slowly kind of stepping away from my role as running the Compass Lectures. And I'm glad to have a wonderful team of people who are keeping this lecture series going. So I want to, thank the Compass Lectures team for putting this on. I want to thank the audience members for attending, because if we don't have attendance, these lecture series will end. And I also want to thank any Cal Nerds representatives for letting us use their space for the lectures. All right, so now for the actual talk. So I'm going to be talking about tunneling two-level systems in amorphous oxide films. So this title has a lot of jargon in it, and this is a no jargon lecture series. So I want to make sure that kind of the ultimate goal of this talk is that you understand what this means and like why this is relevant to current research. So once I figure out how my slides advance, there we go. So just a brief overview of the talk. So because this is a talk geared towards undergrads, and I know that we have a lot of people with a lot of different experience in physics, this is a physics talk. I'm going to cover very, very briefly cover a few physics topics as like a prerequisite. The second part, which is the bulk of the talk, is going to be kind of an introduction to glass physics, which is what I study. And then the third, if we have time, is I'm going to go into some results of some of the work that I've done. And I will say, feel free to, if you have questions at any point, feel free to raise your hand. And if anybody on Zoom has questions, let me know as well. All right, so first, kind of the overview of some background concepts. Now, I will warn you that to give a proper overview of glass physics, I would probably need like a few lectures. So I'm going to go through a lot of this really quickly, and I'm going to hand wave a lot and skip a lot of things. But these are all typical topics that you would see in in your intro physics classes. So first thing is potential energy. So I want to first talk about classical physics because this is what we're all familiar with. This is the physics of everyday objects. So we talk about something called potential energy pretty early in physics. There's lots of different types of potential energy. Essentially, potential energy is just a way of storing energy. So we have gravitational potential energy. This is you pick up something and you let go when it falls. We have elastic potential energy. So this is what happens with springs. If you have a spring, typically it has kind of an equilibrium length. If you compress it or you stretch it out, you're adding energy to that. You're adding potential energy to that spring. There's also electrical potential energy where you have charges that repel each other or attract each other, and there's a potential energy associated with that as well. There's lots of other types of potential energy, but the main thing to kind of take away from the classical state is we can have any energy levels that we want. If I have this roller coaster up here, I should use the pointer. If I have this roller coaster up here, this roller coaster can start from rest. It can start from 1 mile an hour, 1 meter per second, 2 meters per second, whatever, any kind of continuous energy level. We have no restrictions there. However, when we get to the quantum state, and again, I'm gonna skip a whole lot of physics to get to here. When you put quantum particles, and I should say, quantum mechanics is the area of physics where we deal with very small things on the size of atoms, subatomic particles, and the physics looks a lot different than what we see with cars and planes and stuff like that, large scale objects. And so it turns out that in quantum mechanics, when you put particles in some sort of potential energy well, you're going to get quantized states, meaning that the particle is only allowed to have very specific energy levels. And we see this in a bunch of different systems. You take an intro quantum class, you're going to study the particle in the box, the infinite square well. You also have the harmonic oscillator, which this is the same kind of 1/2 kx squared shape that we saw with the spring. We also have something like in atomic physics, like the hydrogen atom, you have certain energy levels that the electrons are able to exist in. And the important thing with these quantized energy states is that the transition between the states, the distance between the states is a fixed number. And so it can absorb or emit certain types of radiation or interact with the environment based on those energy levels. All right, the second topic is quantum tunneling. We're gonna start increasing difficulty here. Quantum tunneling is a phenomenon that we see in quantum mechanics that we don't see in classical mechanics. So the idea is, from the classical point of view, if I have a wall, I cannot walk through the wall. You don't need to take any physics to realize that. So we have this kind of potential barrier where, in order to cross this barrier, I need to use here so Zoom can see me. In order to cross this barrier, you have to have enough kinetic energy to be able to actually go over the hump. If you do not have enough energy, you're going to go part way up, and then you're going to turn around and get pushed back. You're going to get essentially reflected. And so things work a little bit differently in quantum mechanics, because in quantum mechanics, instead of having individualized particles, we have this idea of a wave function. Wave function is more or less like a probability distribution. It tells you where you're likely to find the particle. You have to make an observation to actually see where the particle is, but the wave function is a function that covers all the space, and it tells you with high probability it gives you a probability density of where you should expect to see a particle. And in the quantum point of view, this wave function looks kind of like a spread kind of like a Gaussian in this picture. And when you hit the wall, the wave function, since it covers all the space, some of that wave function can actually leak through the wall and appear on the other side. Meaning here, we actually have like a small probability that a particle can actually go through the wall. So classically, this is forbidden. This is not allowed. Classically, I can't throw a football through a wall. But in the quantum sense, when you're talking about small particles with a potential energy barrier, you actually have like a probability of tunneling. And we call this interaction tunneling, going through the wall. The main takeaway from here is that quantum states may tunnel through classically forbidden regions. So something that we see classically is not going to behave the same in the quantum sense. All right, let's step it up one more level of difficulty: entropy. So entropy is, for me personally, when I was an undergrad taking my intro classes, entropy was probably one of the hardest topics for me to get like an intuitive understanding of. And this is not going to give you that much of a intuitive understanding, but I do want to try to tie it a little bit to what I'm going to talk about a little bit later. So I want to introduce the idea of a microstate and a macrostate. And I'm borrowing this picture from a professor at George Mason University, where they explain they have a system of 4 coins, and so you can put these coins in a box, shake them up, and you have some combination of heads and tails. And so with 4 coins, you have 24 possibilities. And so each of these possibilities, we're going to call this a microstate, and we call it a microstate because it's a kind of a microscopic, a very detailed description of your state. You're tracking each coin and you're looking at like, what is the state of each coin together. We can also look at just how many heads do we have, and that's more of like a summary of the entire system. It's not taking into account what the individual coins are doing. And I want to call that a macrostate. It's a macrostate kind of describes the system as a whole, as opposed to like the individual details. And so in this picture, we have 24 different microstates, but they're grouped into 5 different macrostates. You can only have 0, 1, 2, 3, or 4 heads. You can't have more or less than that. But you can see each macrostate has a certain number of microstates. And so the main idea here is that each microstate has an equal probability. If I shake up the box, each of these 24 possibilities is possible, but because each macrostate has a different number of these microstates, each macrostate has a different probability. And so entropy is kind of a way to connect those 2 ideas, the macrostate and the microstate. I'm going to wave my hands furiously here. I'm going to take, for example, this situation where H is the number of heads. I'm going to define this. Omega of H is the number of microstates associated with that heads. In this case, if H is 4, the number of microstates is 1. If H is 3, the number of microstates is 4, etc. If I had, for example, 100 coins, a lot more coins, there's a lot more macrostates, or a lot more microstates and macrostates. With 100 coins, I have 101 macrostates, 101 different possibilities, number of heads. I have something like 10 to the 30 number of microstates. And so it turns out that if we're counting microstates, it gets to be a very large number very quickly. So we tend to look at the log of those. And I think I might have deleted that line. That's fine. We tend to look at the logarithm of the number of states because it's such a large number. It's easier to look at the logarithm. I'm going to wave my hands a lot, and the entropy is proportional to the log of the number of states. Okay, so the main takeaway here, if none of that made sense to you, the main takeaway is in this box. The entropy gives us an idea of the number of possible states that we're in. So if I have a high entropy glass, for example, that means there's a lot of different configurations that correspond to that type of glass. If I have a low entropy glass, there's only a few types of configurations that are available. Again, if this made no sense, when you take your thermal physics class, you'll learn a lot more about this. Summarizing these 3 main takeaways, quantum systems, energy levels are quantized. Quantum systems, we allow tunneling, and entropy is a way to give us an idea of number of states available. Good. Yeah.
So just, you mentioned that these energy levels are at different levels with respect to, like, they have to be at certain integers or something. So does that mean that if there are different integers, I have a different, like for these quantum tunneling effects, does that mean that I like have a different probability of going through the wall if I have, because you mentioned like going over a barrier with classical particles, so like does that change? Do I have a different probability if I have higher energies like for those quantized states, or?
Yeah, if you have, so comparing it back to the classical case, the more energy you have, the further across the barrier you can go. If you have, in the classical case, you need to have more kinetic energy in order to cross the barrier. In quantum mechanics, we don't have that restriction. We can have less kinetic energy than the height of the barrier, for example, or the particle energy can be less than the height of the barrier. And that's going to correspond to, there's a certain tunneling probability associated mostly with the size and the shape of the barrier, but the energy, the higher up in energy you are, the more likely you are to tunnel through also. All right, other questions right now? Okay. All right, so next is going to be kind of the bulk of the talk, which is like the introduction to glass physics. So a lot of what I study. So first, I want to talk about crystalline versus amorphous materials. So typically, if you take solid state physics or you're interested in semiconductor physics, you start off with crystal structures. In this case, here I have an alpha quartz silicon dioxide crystal. If you were to take just like one chunk of this crystal and you were to move to a different part of this crystal, you're going to see an identical copy. You have a periodic structure that's repeated throughout the entire crystal, throughout the entire film, or whatever you have. And so we say that we have long range order, meaning if I know what's happening here and I move over 1 centimeter, I know exactly what's happening 1 centimeter over. I know exactly the structure. For amorphous materials, what ends up happening is we do not have this long range order. We have kind of a more or less random arrangement of the atoms. It's not quite random in the sense that we have this underlying structure for SiO2. We have these SiO4 tetrahedra, meaning each silicon atom is bonded to 4 oxygen atoms, and that forms a tetrahedron. And that tetrahedron is what is randomly kind of arranged throughout the material. So even though it's the tetrahedra are kind of randomly arranged, we still have this internal structure that doesn't go away. So despite it being an amorphous material, there is still some sort of structure in between. All right, so this explains kind of the amorphous part of the talk. So a little bit more about the properties of glass. So traditionally, the way that glass is formed, it comes from supercooling a liquid. So if any of you have ever seen glass blowing or have done glass blowing, you end up melting the glass. You have this kind of ball of molten silicon dioxide. You form it into whatever shape that you want, and then it cools down and it forms a glass. That's not the case for all materials, but silicon dioxide is a material that likes to form a glassy state. Typically what happens, you have 2 paths. If you start from a liquid, you cool it down. The typical path that we're used to is you get to some melting point or some freezing point. At this point, all of the atoms are going to arrange themselves into a crystal. During this time, the entropy is decreasing. There's fewer different configurations, fewer different ways that you can arrange your atoms into the crystal as you go down, and eventually you get fully crystallized. Every atom has found its correct position, and now as you continue to cool, the entropy that is lost is due to like vibrations and electronic effects. But down here, this bottom line here is a crystal, fully formed crystal. There are materials where you can bypass the crystal altogether and not allow it to form the crystal structure, and you get what's called a supercooled liquid. So it's still a liquid. It's a liquid that's below the freezing point. There are some cool YouTube videos about like supercooling water that you can look up, where you get a super cold water bottle and then you like hit the water and it instantly crystallizes. It's pretty cool. Eventually what happens though is as you're cooling down and you're removing energy from the system, the dynamics of all the atoms slows down. So they basically slow down and stop in the kind of liquid arrangement where it's a bit more disorganized. And then you end up getting a glass. Once the motion is stopped, you no longer have any of this motion in the atoms. There used to be this idea of a Kaufman paradox. This scientist named Kaufman theorized that, if I keep cooling, theoretically, I should be able to cool it to the point where my liquid has the same entropy as a crystal. This paradox was evaluated by this idea of the glass formation. So the glass formation actually prevent these 2 lines from ever actually touching. All right, then we have a second picture of how we can look at these materials. So on the left, we have the entropy temperature picture, and on the right, we have kind of a potential energy diagram. So think of this as kind of like the roller coaster track from before. I will say that this is a very loaded plot. There's a lot of stuff in here that I'm going to skip, but this axis on the bottom, this Z star axis, represents the XYZ position of every atom in your glass, all collapsed into one axis. So this is a very, you can think of this plot as like one slice through a very large, 3 to the power of 10 to the power of 23 dimensional space or something like that, very large space. But the main thing is that at the bottom of each of these wells is a quantum state, as I mentioned before. So each of these states at the bottom of each well represents a different configuration of atoms. So in a crystal, every atom has a correct position, and there's one crystal structure, or there might be several, but there's one crystal structure, and you have one state way down here that's there are no other states nearby. That's the state that you're in. But for all of these other states, these are all glass states. These are all amorphous states. And you have some states that are nearby each other. They're very close to each other, and you can actually change states by having atoms move around in your material. This leads to a lot of properties where we can actually see whether we have a glass versus a crystal. One of the things that we see is in the heat capacity of materials. So if you take a solid state physics class, you're going to learn about heat capacity. Heat capacity is the idea that if you add energy to a system, the temperature of that system is going to increase, and the heat capacity is the ratio of that change. For insulating materials like glass, typically or non-glass, you have a heat capacity that depends as T cubed, meaning if you plot T cubed versus heat capacity, you get a line. But for glasses, we actually don't see this. We actually see a linear term. We get this extra T plot, and I'll show some plots where this is going to actually make a difference. So this red term here only occurs in glassy materials, only in disordered amorphous materials. You don't see this in crystals. And so what happens is we have several of these states that are really close to each other, and we have these two neighboring states called I call them tunneling two-level systems. They're two-level systems because you have two levels, you have two energy levels, and you actually at low temperatures, you're going to be able to tunnel between these two states. So despite the energy level being lower than the height of this potential barrier, you're actually able to tunnel between this. And in glasses, since we're talking about a large cluster of atoms, each of these states represents an entire group of atoms moving, not just one individual atom moving from place to place. So here we have two different configurations kind of going back and forth. There's two kind of energy regimes that we want to look at. At low temperatures, tunneling is the main effect. We don't have enough thermal energy to excite this. So I'm not showing all the states, but earlier I showed a harmonic oscillator that had several states. If you heat up your system and add energy to the system, you can actually excite up that ladder. But at low temperatures, you're going to be at the bottom rung of that ladder. And so if you're at the bottom rung of this ladder and the bottom rung of this ladder, you should not be able to see each other. But we've seen in several decades worth of experiments that you're actually able to tunnel between the two. At higher temperatures, if we heat up the system like room temperature, we actually have enough energy to jump across the barrier. So it's kind of like having the roller coaster that has more than enough energy to go over all the hills. What is the purpose of this? Why do we care about this? So it turns out that these two-level systems, they introduce noise into a glass that you have. These are able to, in order to go between these two states, we can interact with vibrations in the material, which we call phonons. So you may have heard of photons, which are light particles. Phonons are lattice vibrations inside of a material, so sound waves traveling. And so a sound wave can go and hit this configuration over here, and it'll jump over to this other configuration. Or it can go from one configuration to the other and then release a sound wave inside the material. And so when it comes to certain applications, this can be an issue. So we have two applications I'm highlighting here. One is the LIGO experiment. Who's heard of LIGO here? Okay, cool. So LIGO is I forget what the acronym stands for right now, but it is a gravitational wave detector. So what happens is when you have two black holes that swirl and collide, they send kind of a ripple through space-time, which is a very, very, very small ripple that we can barely detect. So we have these long 4-kilometer long arms that hold a laser beam. We shine a laser in one. We shine a laser into a mirror. This laser splits. Some of it goes up. Some of it goes to the right. It reflects back, and then we get an interference pattern. And based on that interference pattern, we can see whether the length of each of those arms changed at all. And the idea is that if a gravitational wave passes through Earth, you're going to see one of them shrink relative to the other, and you'll actually see the interference pattern change. the important thing for this experiment is at the very end, you have these very large, highly reflective mirrors. And it's important that you don't have any mechanical loss in those mirrors in order to have a very high efficient signal. And so one of the applications of understanding tunneling two-level systems is to be able to understand how to reduce the noise in these systems. We want to make sure that if we want to have a very sensitive, high resolution detector, we want to minimize any sorts of noise that's coming up. At lower temperatures, at cryogenic temperatures, we have a lot of current research is going into quantum computing. That's kind of like a really big area of research right now. And you have these large quantum computers that are meant to hold quantum states. And many of these computers have to be held at very low temperatures in order to be viable to hold the state. And so there's a lot of metallic components that can oxidize. And so specifically with my material, since I'm working with oxides, the oxygen in the air can cause oxidation or rust to happen on some of these materials. And that is actually enough to introduce TLS and noise into these quantum systems. And this leads to qubit states being decomposing over time. So you're not able to hold like a quantum state, a qubit for as long as like a traditional computer. Okay, and so this explains the tunneling two-level systems part of the talk. Yeah.
Just a quick materials on Zoom. It's about mirrors, not like it's like regular mirrors. The question is, if glass used in mirrors is an amorphous material, why does it reflect light so well?
So the one advantage of having amorphous materials is that since you don't have a crystal, you don't have any weird crystal planes. And so in a crystal, you have crystal planes that have to align. You have to make sure if you want a very flat material, you have to align your crystal plane to be perfectly flat. And the mirrors of LIGO are on the order of a meter and a half in diameter. That's very impractical to use with crystalline materials. Ideally, a crystalline material would have 0 TLS, so that would be an ideal system. But in terms of practicality of creating it, that's not really possible. Versus with amorphous materials, you can make a perfectly flat mirror without having to worry about a specific orientation or anything like that. Cool. Other questions? Okay. So next, I want to go into kind of classifying some of these glasses. And so silicon dioxide, this is kind of the typical glass that we're all familiar with. Windows, eyeglasses, drinking glasses, typically made of silicon dioxide. Oftentimes, these are doped with other elements to make it more rigid so it doesn't break as easily. But it's a system of all silicon and oxygen atoms. Typically in a crystal, you have a very well-defined bond angle and bond length, but in an amorphous material, you have a little bit of a distribution of angles, and this is what allows us to have an amorphous structure as opposed to like a very rigid crystal structure. Oxide glasses, typically, I study simple oxide glasses where you just have a single metal or semiconductor and oxygen. There's a lot of research on like of more complex oxides where you have multiple metal ions, but then in that case, you also have a lot of electronic effects that I'm not really interested in studying, and it just makes the project a lot harder. But for the simple oxides, I'm able to classify them into 3 categories. So the first is network formers. This is like typical glass that we work with. It's easy to supercool the liquid into a glass. So silicon dioxide is like the main one there, but there's some other examples down here. We have network modifiers. So what you can introduce these into a glass, and these actually break up the network. And what happens is it breaks some of the, for example, silicon oxygen bonds. It'll break some of those bonds and it'll let the oxygens kind of hang. So typically oxygen in a pure silica film, oxygen has 2 bonds. In this case, adding a modifier kind of breaks some of those and lets some of them have 1 bond. Network intermediates are kind of in between. They can serve either case. This is a picture kind of showing what's going on. In the top one, I'm using sodium oxide or soda glass as the modifier, and so we have these kind of floating Na plus ions, and then we have these yellow oxygens that only have 1 bond instead of 2. In the bottom case, we have lead oxide being added, and lead actually substitutes. It takes the place of the silicon, and so it is able to incorporate itself into the glass. All right, and so this explains the oxide films part of the title. Okay, that's a lot of information so far. Any questions? Yeah.
One more from Zoom. Could you explain again how the tunneling to the behaviors qubits and introduces noise?
Yeah, so I mentioned before that when we have the two states, we actually have clusters of atoms moving between states. And so in a cubic system, you don't want anything interacting with your qubit. If you have an oxide forming on some of your electronics that naturally are going to form these TLS, these two-level system states, in the case that you are going from a high level to a low level, that's going to introduce a lattice vibration, and that poses a potential danger to your qubit state. I'm not an atomic physicist, so I'm not super familiar with it, but from my understanding, it's the interaction between the TLS and phonons that eventually cause the qubit states to decohere. All right. So in the last few minutes that I have, I just want to just quickly go over some of the actual work that I've done. And so in terms of like actually producing these glasses, I talked a lot about liquid quenching glasses. So starting with a liquid, cooling it down until it forms a glass state. That's not what I do. I don't actually do that. So I use vapor deposition to form glasses. And so this is starting from a crystalline source and by some means removing atoms from that source and placing it onto a substrate and forming a film from in that way. Our lab focuses on 3 different methods. So thermal evaporation is the simplest. You heat up the material until it melts or until it vaporizes or it sublimates. It creates a kind of plume of atoms, and you put your substrate at the top, and all the atoms kind of attach to the substrate. Electron beam evaporation, instead of heating it up, you have a beam of electrons that you accelerate with a magnetic field. You hit your source, it knocks atoms off of your crystal source, and then hitting the substrate, you form an amorphous film. And then third is magnetron sputtering. So in this case, you form a plasma, and you're able to accelerate these larger ions into your source, kicking off atoms and forming a film. The reason why I use vapor deposition is with liquid quenching. I mentioned that we have all these states, all these glassy states. Liquid quenching tends to get you stuck on one of these higher states, these higher entropy states. Notice like at this level, there are a lot of states available, but as you go down in the entropy, you also go down in this energy level and there's fewer states available. And vapor deposition allows us to directly grow films that are in one of these lower lying states, which is closer to what we're looking for low TLS materials. These materials are studied in 2 different ways. So I mentioned calorimetry. Previous members of our group developed these calorimeters on a chip, these small half a centimeter or a half centimeter nanocalorimeter devices. And so you can deposit your film onto the center of this device, and with this complex set of thermometers and heaters, you're able to figure out the heat capacity of your film as a function of temperature. So at various temperatures, if you cool down your system, the heat capacity is going to be different. And based on the shape of that curve, we can get an idea of the density of TLS in the film. Another major one that I've focused on in my later years of the PhD, I've been using mechanical loss. So in this case, I grow a film onto this device called a double paddle oscillator. So this is a single crystalline silicon substrate that has a really weird shape. It has a head, a neck, wings, a leg, and a foot. I deposit, it's kind of hard to see here, but I deposit a film directly onto the neck of this substrate. And when in collaboration with some folks at the Naval Research Laboratory in DC, we're able to measure mechanical loss in this film. And what they do is they clamp down the foot, and they set the wings and the head of the DPO to oscillate in a anti-symmetric oscillation. And this causes the film to twist. And basically setting this as a ring down, think of a damped harmonic oscillator, it'll dampen over time, and we're able to measure the quality factor and the quality factor Q, and the internal friction is the reciprocal of that value. So Q inverse is the internal friction that I'm interested in seeing. And so looking at internal friction of glasses over several decades of research, it turns out that all of these glasses have a typical shape of their curve. There's an internal friction plateau between about 0.1 and about 10 Kelvin. So this is very, very cold temperatures. And it's been seen as kind of a universal glassy range. All of these liquid quench glasses have this this plateau, and this plateau falls between specific values 10 to the minus 4 and 10 to the minus 3. And so ideally, we're trying to find some sort of glass that would fall below, the plateau would fall below this region. And so it's believed that the height of this plateau is proportional to the number of TLS in your system. So the lower this plateau is, the fewer of these tunneling systems that we have. And so at lower temperatures, this is more relevant for stuff like quantum computing because those operate at cryogenic temperatures. At higher temperatures, this is more relevant for things like LIGO, where the mirrors are at room temperature. And so we see different behavior at different temperatures. So looking at some previous work from our group, we did see that with, the range is not here at all. So there's like a pink range between 10 to the minus 4 and 10 to the minus 3. We saw that with increasing deposition temperature, vapor deposition temperature of the substrate, we're able to actually decrease this plateau below the universal range. And so our group with amorphous silicon, so not silicon dioxide, but just pure silicon, we were able to see that it is possible that these states do exist, that this idea of an ideal glass, a glass that has much fewer TLS than a typical glass, we're able to actually see this at at high growth temperatures. All right, that slide is in the wrong place. I'm going to speed through this last bit. So for my PhD, I've studied specifically oxide glasses, and so this is kind of the list of glasses that I've studied. I'm finishing up this last project now. After growing these films, we characterize them by various ways. So this is how we know that we actually have what we think that we grew. If I grow SiO2, I should have 33% silicon atoms and 66% oxygen atoms. And so we have various tools like Rutherford backscattering spectroscopy to verify that composition. We have different ways of understanding the structure, different types of Raman spectroscopy, high-res TEM. We do calorimetry and other ways of actually measuring the TLS density as well. All right, and just kind of showing a little bit of this heat capacity data from the past. We saw that with looking at silicon, when we have the crystalline silicon, this is the heat capacity divided by T cubed. So if it's a crystal, heat capacity should go as T cubed, and that's what we see here. The curve is flat as we get closer to zero temperature. But for the actual glassy materials, T divided by T cubed is 1 over T squared. So we should see these things blow up as we get closer to zero, and that's what we see. And based on these heights, we can actually fit the curve and extract the actual values of the TLS density, which I did on the side over here. We saw similar results with amorphous silica. We see that all of these curves, they start to shoot up as we get closer to zero temperature. If they were crystalline, they would be flat. Similar idea with looking at the internal friction of silica. We see that increasing the substrate temperature during growth actually decreases the plateau level. So we are seeing a decrease in the TLS density, but we're not seeing anything that's ultra low or anything that's significant for the applications that I mentioned. Amorphous alumina, this is another case where we, in addition to increasing the substrate temperature, we also did some post-growth annealing, meaning we just put it into a furnace, set it to a high temperature, and kind of let the atoms that are already in the film kind of wiggle around and find their new positions. This caused the internal friction to go down slightly in each case, but nothing significant below the universal range. Again, this universal range is about, it ends around here where this green line is. We would expect to see things several orders of magnitude below for it to be useful. I'm going to skip that step. And so, yes, in summary, yeah, we study amorphous materials. I study oxides in particular. This is a very interesting kind of field to study. This is if you go into condensed matter physics or solid state physics, you're probably going to deal with crystals. That's the easier thing to study. But I think there's a lot of really interesting physics in the amorphous systems. There's a lot of unexplored territory in the amorphous systems because they are a bit harder to study. And so, yeah, the idea was that with these glasses, I would want to figure out a way to eliminate TLS. After years of experiments and study, I realized that I have not been able to do that with my films, and that's fine. Research is not always going to be in the direction that you want it to go, and that's okay, because I did it. Okay, and with that, I'm going to leave it there. So let me know if you have any questions. Yes. They were candidate materials for LIGO. So currently LIGO uses silica and tantala, I believe, silicon dioxide and tantalum dioxide or tantalum oxide. It's a complicated number. And I should have mentioned that the mirrors that they use it's what's called a Bragg reflector. So you actually have an alternating set of layers of high index of refraction and low index of refraction materials, and you stack them up, and you're able to get a very high reflectivity mirror. And so there were talks about possibly changing the material inside of there as to improve the mirrors, but and aluminum oxide specifically was a candidate material, but based on some old sputtering data, but it turns out after the work that I've done that it's not actually feasible.
Why is it instead of the magneton sputtering system? Because I think that for magneton sputtering we have densities, right?
Yeah. So well, this is something that I'm actually trying to figure out now with my Illumina films. We did do both sputtering and e-beam to compare the two, and it turns out that from what I've seen, the e-beam films are more dense from measurements, but it turns out that e-beam produces rougher films, so they're not as flat, and so the density has very large error bars and is not as reliable. So, but typically for most materials that we've seen, sputtering should give you a denser film just because it's a more energetic process. You're hitting it with larger ions than just electrons. But yeah, that's kind of it. Yes, it's material dependent. Yeah. Other questions? Yeah.
So you mentioned doing all these experiments where you by increasing the deposition temperature, you actually had a better, decrease in whatever that friction constant of internal friction. Is that what it was? Do you have a mechanistic explanation for why that would happen?
Yeah, so the idea is that when you're growing a film, you have, and I kind of skipped through this, but I may have a backup slide actually. Yeah, this kind of explains it. So there's this idea of diffusion, surface diffusion and bulk diffusion. So how well can the atoms within the film and on the surface of the film move? By elevating the temperature, you're able to increase the mobility. And it's actually, the important thing is the ratio between the bulk mobility and the surface mobility. The surface mobility are all the atoms that are coming in during deposition. The bulk is what's already there. And so if you have a high surface mobility and a low bulk mobility, as the atoms are coming in, they're able to kind of find their way around. And so we're able to tune that with deposition temperature.
Does that not help make the system more crystalline in the end, and you're still cooling it quickly after the deposition?
So I have seen that in particular Illumina, because I'm writing a paper right now on it. There's a maximum temperature above which I start to see in the sputtering, we start to see crystallization. And so we were limited, the data that I showed earlier, we were limited to certain temperatures based on, for the sputtering, we were limited to 500 Celsius because at 550, we started to see signs of crystallization, and that's what we're trying to avoid altogether. For the E-beam films, we didn't have crystallization as the issue at high temperatures, but we actually saw that at high enough temperatures, you actually don't get any deposition. Like the atoms just kind of like bounce off the substrate and don't actually form a film. Yeah. Great question. Yes.
So usually when we run this, we basically, so there's a trick to just run very high power to pump all your states to the higher state, so it kind of suppress the tailless noise. Do you not do that in LIGO? Like it shoot very strong laser, kind of.
Well, I think with LIGO, the laser that you're using is the signal that you're using the laser as part of the signal. You're looking at the interference of the two laser beams. So you can't really. I would have to think about that. We're typically not driving the mirror in any way. We're not like powering it or anything. We're just it's stationary. It's seismically isolated and everything. So we're not actually like touching the mirror. So whatever the laser is doing to the mirror is, we can't really control that easily. As opposed to, I think, in like qubit systems, you have more control over the individual parts. From what I understand, I'm not a qubit person, but
Can you clarify that you're just talking about the initialization of the coherence? Say what I think the problem is the decoherence, right? So wouldn't you just, isn't that just you resetting the problem? When you're setting like you're hitting with a high laser, aren't you just resetting the system?
I'm not sure this is a good analogy with qubits and mirrors. I don't know, but the kind of simple way to understand is, so you're kind of constantly sending energy into the system and see how much comes out. That's kind of reflection, right? And if you just send a very high energy, you move all the kind of lower state to the higher, and they will never come back. So you cannot jump between them. And then the problem is not that you can go high or go low or what's the distribution, but rather you want them to jump around. That's noise. Or at least that's the problem for qubits.
Okay, gotcha. Yeah.
So they can be at that state as long as they don't move.
Okay.
Yeah.
I think the mechanism is a bit different for mirrors and qubits, from what I understand with qubits. Yeah, essentially with the mirrors, it's the laser is hitting, and some of that, and there's like a tiny amount of that energy that's being lost and kind of just being lost to the mirror itself, and that's what we're trying to minimize. Yeah. All right, thank you very much.